A graph is a data structure used to represent relationships between objects. It consists of vertices, nodes, which represent the objects, and edges, which represent the connections between them. Graphs can be directed where connections have a direction like one-way streets, or unidirected where connections go both ways. They are commonly used to model networks such as social media connections, road maps, and computer networks. In programming, graphs are typically implemented using structures like agency lists or agency matrices to store how nodes are connected. In our roadmap example, to find the shortest path in a graph, you start from a chosen node and explore neighboring nodes while keeping track of the smallest known distance to each node. Edges have different weights. Algorithms like Dijkstra's algorithm are usually used for it, which repeatedly selects the node with the smallest known distance and updates the distance to its neighbors. By continuing this process until the target node is reached, the algorithm determines the shortest path through the graph. Any adjacency matrix is a way to represent a graph using a two-dimensional array. Each row and column represents a vertex, and the value at the position I, j indicates whether there is any edge between vertex I and vertex j. In any unweighted graph, the matrix usually contains 1 if a connection exists and 0 if it does not, while in a weighted graph it might store the weight of the edge. This representation makes it very fast to check if two vertices are connected, but it uses more memory because the matrix size is always v times v, where v is the number of vertices. The adjacency list, on the other hand, represents a graph by storing for each vertex a list of all the vertices it is connected to. Instead of using a matrix, the graph is typically stored as any object, map, or array where each key is a node and its value is a list of neighboring nodes. This representation is more memory efficient than an adjacency matrix, because it only stores existing edges rather than all possible connections. Adjacency lists are commonly used in practice because they work well for sparse graphs and make it easy to iterate through a node's neighbors during algorithms like BFS or DFS. To implement adjacency matrix in Java, all you have to do is to declare two-dimensional array and allocate new memory space based on the number of vertices. To add a connection, just assign 1 to the specific node where u is the initial node and v is the final. Do the same in the opposite direction if the graph is bidirectional. For adjacency list, keep track of number of vertices, create new map where each vertex has its own array list of vertices that is connected to. To add connection, just find vertex based on the map key and add to the list. Do the opposite for bidirectional graph. Subscribe for more videos like this one.